welcome today's lecture. Today we shall continue the same design of slabs, and that is part 2. So, and this is our lecture number 15, design of slabs, part 2. Okay. So, let me first remind you the problem that which we have started solving in the last class, that design of one-way slab. We have started with the design of one-way slab. Design a simply supported RCC slab for a roof of a hall 3.5 meter into 8 meter inside dimensions with 250 millimeter walls all around. Assume a live load of 4 kilonewton per square meter and finish 1 kilonewton per square meter. Concrete grade M20 and steel Fe415. Just to show you what we have done so far, how far we have done. So, we have done the calculation of factor loads step 1, and that we have done on the basis of say span by depth ratio. Okay. The next one, we have calculated dead loads on the basis of assumed thickness of the slab, and finish already we have taken 1 kilonewton per square meter, live load 4 kilonewton per square meter. We have to calculate effective span, that also we have calculated, and effective span we have got out of these two, the lesser one, that is 3.64 meter, and total load per meter width of the slab, that is 49.14 kilonewton. And finally, we are getting that ultimate moment and shear, which we have to do it for design, and that we have got it mu equal to 22.3587 and Vu, the shear force, 24.57. So, let us start the check. Number 3, check depth for bending. We are considering bending first. So, we have to consider bending here. We shall use the same beam formula of rectangular beam. Only difference, we are taking 1 meter, that means 1000 millimeter, and this is your overall depth, which is 160 in our case. We have to provide the reinforcement in the slab, that we have to provide the reinforcement in the slab. So, we are taking the rectangular slab, that rectangular beam 1 meter width, and depth we have assumed 160 millimeter, and that we have to check whether that is sufficient. So, mu equal to 0.138 FCK BD square, D equal to root over mu by 0.138 FCK times B. Moment equal to the moment we have calculated, that is 22.3587 kilonewton meter. So, moment we have calculated 22.3587 kilonewton meter. So, 22.3587 into 10 to the power 6 Newton millimeter divided by 0.138 times 20 times 1000 equals 90 millimeter, and which is less than 140 millimeter, the effective depth that we have got it. So, D equal to 160 minus 15 minus 10 by 2, which is coming as 140 millimeter. This is the one that we are providing, and so D computed, to make it clear, D computed equal to 90 millimeter less than D provided equal to 140 millimeter. It is quite high of course, but anyway we shall come back again. So, this is your that check, so which is all right, but not economic. Number 4, check for shear. So, what about tau v? Tau v equal to VU by BD equals, just once more let me show you that VU equal to 24.57 kilonewton. So, VU 24.57 into 10 to the power 3 Newton divided B 1000 times D 140, which comes as 0.1755 Newton per square millimeter. Table 19, IS 456 2000, it gives for less than equal to 0.15, that is equal to that. This is what is this one? This is AST 100 AST by BD. For this 0.15%, we get tau c equal to 0.28. This one we will get it in table 19 IS 456 where tau c 0.28. So, tau v less than tau c, so we do not need any that shear reinforcement, that means we do not need any stirrup. Okay. So, that is why we do not provide any stirrup, but for other purposes we may need it. Okay. Number 5, calculation of steel areas. So, directly we can calculate this, or we can go from the mu, that formula, or directly we can remember this formula 1.2 minus root over 1.2 whole square minus 6.6 mu by FCK BD square. So, this formula we can directly use it if you can remember, otherwise you can start from the first principle, that using the same formula. So, 6.6 mu by FCK BD square equals 6.6 times 22.3587 into 10 to the power 6 Newton millimeter divided by 20 times 1000 times 140 whole square, which comes as 0.376. Therefore, x by d equal to 1.2 minus root over 1.44 minus 0.376 equals 1.2 minus 1.0315 equals 0.1685. So, what about your z? X by d, this is less than 0.48, xu by d, this is less than 0.48. Let us write down, this is less than 0.48. So, we can calculate now the lever arm, we can now calculate the lever arm. So, what about your lever arm? Lever arm z equal to d 1 minus 0.416 x by d equals d equal to 140, 1 minus 0.416 times 0.1685 equals 130.186 millimeter. What about then area of steel? area of steel equal to mu by 0.87 Fy times Z equals 22.3587 into 10 to the power 6 divided by 0.87 times Fe415 times 130.186, which comes as 475.6 millimeter square. What about the spacing? Spacing required, because here we do not provide the number of bars, here we provide that how many bars, at what spacing you will provide the reinforcement. Unlike say your beam where we provide the number of bars, 3 bars, 4 bars like that, but here we provide that 10 millimeter at the rate of that spacing we provide, the way we have provided stirrup. So, spacing required 1000 times so how many bars we require? 475.6, that is the area of steel. Individual bar, let us take say 10 millimeter. So, we can get S bar if I consider. So, we can get here 78.5, right, equals 78.5, and which comes as, we are assuming that we shall provide 10 millimeter bar, and we are getting here 165.05 millimeter. So, we can provide 10 torr at the rate of, we can provide 160 also, but let us provide 150. So, 150 millimeter center to center, and the area of steel provided, that is coming as 523. So, this is your 10 torr at the rate of 150 millimeter center to center, area of steel this is provided, and area of steel this is computed. One is computed, another one is provided. So, you have to check that how much actually you are providing. So, we are providing here 523. Okay. So, now we can check. So, let us see the, so area of steel 500, or let us say make it very clear, area of steel provided equal to 523 square millimeter. Okay. So, percentage of steel equals 523 into 100 divided by 1000 times 140. 1000 is the width and 140 is the depth, of effective depth, which comes as 0.373%. There is one which is called FS, is a factor point, because we are interested, we would like to modify, we have assumed that L by D 25. Now, we would like to check, we have that L by D, we have started with L by D, that is 25. Now, we would like to check whether that is sufficient or not, because we have to control the deflection also. L by D 25 we have assumed, if it is less than 25, if it comes, then we have to change the depth, but if it is more, if we do not consider the economic consideration, then we can stop there. Otherwise, if we consider okay, it is too much, then obviously again you have to reduce the section. So, whatever the way our code says, let us see. So, we shall use this table, or sorry, figure 4, modification factor for tension reinforcement. We have given the tension reinforcement, that which AST that we have calculated, and that here we are getting 0.713%. So, for 373, for 0.373%, what we shall do, there are so many stress level, Fs 120, 145, this is 145, 190, 240, 290, but it is not related with, directly not related with the Fe415. We have to do certain kind of modification. What is the modification? This line, if you do not, if you could not get it, let me write down here that formula. Fs equal to 0.58 FOI, FOI is 415, FOI is Fs equal to 0.58 times FOI divided by area of cross section of steel required cross section of steel required, this one will be required, okay. Last area of cross section of steel required and area of cross section of steel provided. So, we have to directly, we cannot calculate, not exactly 0.58 FOI. So, here we have to do certain kind of modification. So, area of cross section of steel required in our case, area of cross section steel required in our case, that is 475.6, and we are providing 523. So, let me write down here clearly, AST required equal to 475.6 square millimeter, AST provided equal to 523 square millimeter. So, Fs equals 0.58 times Fe415, so 415 divided by 475.6 divided by 523, which comes as 218 Newton per square millimeter. So, we are getting here 218 Newton per square millimeter. So, this is the one, that value through which we can find out the corresponding that modification factor. So, now if we come to this figure 4 of IS 456-2000, we know this is 218 and percentage of steel we are getting here 0.373. So, 0.373 means somewhere it will be somewhere here, it will be somewhere here. So, we can write down so if we write down here, I think if we go something this way, so we can get somewhere here, we shall get it. And what is the value? 218. So, 218, you can see that Fs, it is dependent on the value Fs 120, Fs 145, 190. It means that if you provide more reinforcement, so your say modification factor will also be more. That way also you can little bit you can manipulate. So, anyway, so if we come here, our case will be somewhere here, our case will be somewhere here, this line possibly somewhere almost in the middle zone somewhere, maybe say somewhere here it will be. So, which is coming here, this value that I have computed here, that is 1.55, because it is 1.4. So, I have taken 1.55. So, I can take that modification factor that is equals 1.55. So, L by D equal to 1.55, this is a simply supported case times 20, which comes as 31. we started that assumed L by D, that is 25. So, that means it is from here we can say, that means we can reduce the D. So, in this case that L by, or let us say D will be equal to L by 31. So, which may be okay. So, we can just come back to the effective depth. Effective span, so 3.64. So, 3640 divided by 31. So, which comes as 117.42. That means we can come to this 117.42, and we have seen also that D, that is coming 90. So, that means in this case what we can do, so 120 that effective depth. So, that way we can take it, but anyway let us complete the problem here, but it is that means it comes, the solution is not economic, it is safe but not economic. So, in that case you can take one can again further one can do the problem, and he can again do the next trial and he can modify the section. So, next one, what about the secondary steel? Secondary steel will be AST. Secondary means the other way. That means here whatever the longitudinal steel we are providing here along the span, say this is, if it is along the span, then this is the other side, that is your say secondary steel, or we call it distribution steel, and this is the main steel which you are computing on the basis of your bending moment. So, AST will be equal to 0.12%, that is the minimum you have to provide, times BD. For mild steel it is 0.15, for taut steel it is 0.12. So, 0.12%, which comes as 0.12 times 1000 times, sorry, this is your overall depth, divided by 100 equals 192 square millimeter. Let me check it once more. So, we are getting here 0.12 times 1000 times 160 divided by 100, okay, 192. So, if we provide eight millimeter dia bar, AS of bar, area of bar, that is equal to say, which comes as 50 square millimeter. So, spacing required that is equal to 1000 times 50 divided by 192 equal to 260 millimeter center to center. Okay. So, we can get that area of steel of individual bar, that is 50 square meter. So, on the basis of that we can find out the spacing required, that is because we are calculating on the basis of everything per meter width, that is why you are taking this 1000. Just to refer this one, I think we should refer that there is a clause 26.3.3b. This one related to the spacing of reinforcement. Let us make it here. So, spacing of reinforcement. There are two cases, 3D or 300 millimeter, whichever is less, Another one, this is also including against shrinkage and temperature. There is another one, number 2, this is also including shrinkage and temperature, that is your 5D or 450 millimeter, whichever is less. We shall, in our case it is coming 260 millimeter center to center, so we can provide, which is less than these values, so we can provide that distribution steel that is 8 torr at the rate of, let us provide 260, so let us provide 250 millimeter center to center. So, we can provide 8 torr at the rate of 250 millimeter center to center. Now, finally, we have to show the detailing. For each reinforcement, that reinforced concrete structures, we have to show the detailing. That means, for beams we have to provide the cross section, also the one longitudinal section we have to provide for beams, and also the cross section we have to provide. In the longitudinal section you have to provide where is the curtailment of the reinforcement and how is the steel spacing, all those things it will come, and your cross section will show a typical cross section. That means at which section you are taking along the longitudinal one, that you have to provide. Here also we have to provide this for slab, we have to provide the reinforcement, that detailing we have to provide. Let us take, this is your one panel for which we are considering. And as our problem says, this is the beam, slab supported over masonry wall in both sides. This is the symbol of masonry. Our reinforcement, what we shall provide our reinforcement, please look, I think we can keep the dotted line here. This is the support. Okay. What we shall do, we shall give one reinforcement. Our main reinforcement, how much we have provided our main reinforcement? 10 torr at the rate of 150 millimeter center to center. We have provided 10 torr at the rate of 150 millimeter center to center. And this is our span, that 3640. And it is more than that, but effective span 3640. And this one how much? This one is 3500 plus 250 plus 250. So, clear span 3500 plus 250 plus 250, which comes as 4000, and effective span we have calculated 3640, 3640. What we shall do, we do not provide the reinforcement here, we can just simply provide the reinforcement, say just one horizontal line, but we have to provide the reinforcement at the bottom as well as at the top. So, what we do here in the support also, we shall provide certain nominal reinforcement that we shall provide. If we have to provide that nominal reinforcement here, then what we shall do, we shall calculate, let us start, this is the one we are starting here, one bar, and then it will be cranked and go up like this. We are starting from here, then go up, and this one. The other one, what we shall do, this is one reinforcement. Similarly, what we can do here, the other one, I can start, go up, and this one. That means alternate. So, your reinforcement will be same, the bars will be same, only thing one will be placed this side, another one will be placed other side. So, it will be cranked in one side only. When it will be at the construction side, they will crank in one side, but they will place alternate way. So, I shall get the other reinforcement, I shall get it like this. This is your reinforcement, and it will keep on going like that. So, here, because we want simply supported case, we want this one as 10 torr at the rate of 150 center to center, 10 torr at the rate of 150 center to center. And if we take a section here, let us say this is section AA. So, we can say this is our section AA, and we have to provide the, where shall we crank? What about this distance? If it is say Lx, center to center distance is Lx, then this one will be 0.1 Lx, that is the one, it will be 0.1 Lx. So, in our case, Lx equal to 3500 plus 250 center to center, which comes as 3750 millimeter. So, 0.1 Lx equal to 375 millimeter. So, from the end of the support, that you will crank at 375 millimeter, and both sides you will do it like that. But we have to provide the distribution steel also, like this. We have to provide the distribution steel also, and if we provide the distribution steel, so since you are cutting this section, so we shall get it like that. We shall get it like that, because that all the longitudinal that you say other direction that on cut, so we will get all, say your the circular one, we will get that with respect to the bar diameter. And similarly at the top also. Please note, we have to provide at least 2 distribution steel, at least 2 bars. At the top, to hold the one, at least 2 bars you have to provide, even if it is small, but you have to provide at least 2 bars you have to provide. Now, what about the other side, this side? What about the other side? That means I can take another section, that is BB, and which we can provide, say here, though it is not a good choice. So, generally we provide somewhere here. And this is your that bar. Please note the dots in 2 different sections. Please note the dots in 2 different sections. This is your section BB. If I say this is 1, this is bar type 1, and this is bar type 2, the distribution steel. So, 1 and this is 2. So, here this is 1, this bar 1, and the other one, the dots are 2, whereas here this one is your 2 and these dots 1. So, because we are taking in the other section, so that is very, very important. Whenever you are showing the section, so which side you are cutting, so that is very, very important. and you can see the main reinforcement always, the main reinforcement will have the maximum effective depth. Main reinforcement here, this is your main reinforcement, so that should be the, that should have maximum depth, effective depth. So that's why it is always in the below of the distribution steel. So you have to provide the reinforcement, also we provide the thickness of slab. That is here 160 millimeter. So we should provide the detailing, including the summary of results, one detailing, so that from there at least a draftsman should be able to draw the figure as per the convenience. So he can place it, but we need this, say, one plan and two section. Okay. There is one more thing that is called, so far we have done the UDL, but if we have, say, slabs carrying concentrated load, if the slabs are carrying concentrated load, then what will happen? In that case, we have one is called effective weight method. We have to calculate the effective weight. Generally, it happens for this particular case, generally it happens where we need that we can experience the concentrated load. We can experience the concentrated load in bridges. In bridges, we can, that because the wheel load, whatever we have, that is your, say, concentrated load. So if we take, generally, I think it is worth mentioning before going to that, there are so many kinds of bridges. There are two different types. One is called, say, highway bridges, another one the railway bridges. So these are two different purpose. Highway bridges, there we are having, say, wheel load, and another one we have, say, that is called tracked load. The loading, whatever we get, the one, say, tire, this is your the tire, or it can have, say, some track load that having, say, very little bit longer length. So when we have that impression on the surface of the bridge, how the bridge comes, there is one bridge that is called, popularly used for reinforced concrete, that is pre-stressed girder. I shall, if I get opportunity, I shall tell little bit on pre-stressed girder. So this pre-stressed girder, which we can construct, which we can make it outside. Pre-stressing, it means, I can show you an example. Let us say there is a stack of books which are simply one after another, all the books, not like this. You are keeping the books one after another in this way. Now, if you would like to carry it, what you will do, you have to press it, otherwise it will fall. If what I am trying to say, the books are not placed like this one after another. Instead of that, books are placed like this, and you are pressing it and then you are carrying it. That means you have to compress it that way, and then you have to do it. Here, what happened here, it does the same way. There is one that cable, that steel cables are there, high tensile cables are there, and those are pulled. If they are pulled and if they are restrained on the two ends, then it will try to compress. You are pulling the, there is once a hole, there are two, there is once a hole, through that you have done the casting of the beam, say, and you have kept one hole through the, that your longitudinal section, longitudinal way you have to. Through that, after 28 days, because after that what you are doing, when it is hardened, fully hardened, then you are passing one say pre-stressing cable. Now when you are putting that one, and then what you are doing, you are pulling it in two sides, and then you are restraining something, resting somehow, and then when you have restrained, then it will try to compress. When it will try to compress, so what will happen then? Initially say the beam was like this. I want say something like this. I am keeping say here, I am not going in detail, I am keeping here, I am giving certain kind of say eccentricity E, and this is your force P, which is putting like this. So it will be like that. Due to bending, due to that moment developed, there is a moment developed here, so initially it will be like this. Not that much, but anyway it will try to bend in this fashion, because you are applying that. I am not directly, I am not putting in the center. Instead of that, I am giving intentionally, I am giving this one at a certain eccentricity. So it will try to make one moment that developed, and due to that and also axial force, so what will happen, it will make like this. So what happen here, if you would like to, for failure, if we apply the load like this, then what will happen, it has to first neutralize and then moves. So automatically you can understand that it will take more load. The other one I can give you example, that is your say that cycle, that one, that ring. There also the spokes, that whatever you are using, they are also, if you have noticed, you will see there also they are doing certain kind of pre-stressing, because all the say your spokes, they always rotate like that, and they are doing that pre-stressing, and that is why it does not bend. Otherwise what will happen, it will just make certain kind of say bending of the your ring. So there also they are doing the pre-stressing. So this is the thing what they are doing. But anyway, we are going little away, but anyway, just to conclude this pre-stressing, this is called pre-stress girder, and so we can go say 20 meter, 25 meter, 40 meter, which we shall not be able to do it by reinforced concrete. Reinforced concrete beams, that one we cannot go say 5 meter, 6 meter, 7 meter, maybe we can go to say 10 meter, but your depth will be enormous. The depth you have to include, because mu equal to 0.138 FCK BD square. So from there you can find out that what will be the corresponding depth. If we have the span more with the same load, your depth will be more. But here what we do, we use that pre-stressing girder, pre-stress girder we use it, and that can go say 40 meter also we can go, and depth will be say your 1 meter, 1.5, something like that it can happen. And we use number of cables, and in bridges we use it. So when we have girders say like this, there are so many, maybe say the bridge having say 6 girders. If you notice nowadays say bridges, when if you go say by train itself, always in the there will be always one another highway bridge at least. So if you notice that you can see that deck slab and the depth of the girder, that you can see there is a difference. So that is, now here we are having that wheel load. This wheel load is coming as a say concentrated load. So now if we have the concentrated load here, then what we will do, how shall we take the effective width of the loading. This loading directly, that whatever the impression, we do not take it, we take little more. So how much more we can take it, that we have to find out. So what we shall do it here, in this case, there is always one wearing coat. Now come to the problem here. There is always one this is called wearing coat. This is not reinforced, okay. And then we are having that bridge deck slab. Let us say this is up to this is the reinforcement, and this is the loading, that concentrated load having certain area. we take 45-degree dispersion. Okay. If we take this one as say H, and we have to find out what should be this length A, and let us take this one say your x1. x1 is the impression say in one way, other way say y1. So, x1 times y1, that is at the top, that is the impression x1 by y1, and we can take this is your say d, d is the effective depth. Okay. This is the effective depth. There are two concepts. One concept is that 45-degree dispersion you go up to the top of the slab. Other alternative that one, because this one if we take this much, that means we divide this one, that means your concentrated load, and so you are taking actually moment, if you compute moment, that will be more, because this one, this length is less, so distributed less, so moment will be more, computed moment will be more, whereas if we take this one, then the moment will be less, because it is distributed along this one. If we take this length, then it will be further distributed, so your moment also will be further less. Now, the designers, one type of designer, one class of designers, they take it say up to this, another one they take it up to this. Obviously, I can say they are more conservative. The designers who are using this one up to this, that means they are more conservative than the designer who are taking this one, because here your moment, all those things will be calculated less compared to this one. So, I can further write down. Let us say it is a continuation. So, if we take this length say B, and this is your span, let us say this is your LE, that effective span, and we have certain impression here. This is our impression either from the tire or any other concentrated load, and after dispersion we are getting say like this. This is our A. So, A is the one, this is the support, span means this one span. So, we can assume that there are two girders, one girder, say this is one girder and this is another girder, and this is the, over there is a bridge deck, maybe say 250 millimeter or say 200 millimeter, in that range it comes. But whereas the girder it may be say your 1 meter, 1.5 meter, so that one will be considered as a support. So, A is the one parallel to the this girder, and from the nearest support this distance is x, from the nearest support this distance is x. So, what we can do, this is your dispersed area. After the dispersed area means after the 45 degree the dispersion, this is dispersed area, and we have to find out the effective width BE, let us say. B is the effective width, if we have to find out, and that impression, that one having say at a distance say x from the nearest support. So, how shall we find out that? So, we can say A equal to, either we can write down say x1 plus twice the thickness of wearing coat or we can write down A equal to x1 plus twice, so let us say thickness of wiring cord plus D. There are two options I have told. I have told either it could be up to this or it can go up to the effective depth. So we can write down that x1 plus twice thickness of wiring cord or x1 plus twice thickness of wiring cord plus D. So that we can find out, and our code says BE, the effective width, equal to K times X 1 minus X by LE plus A. So this is one, A I know, X I know, LE I know. So I can find out KX, LE effective span and A. So I can find out the effective width. This is the effective width. Instead of taking it per meter width or anything, so it could be that effective width. So I have got this one effective width, and what is the value of K? This one I shall get it from table 14 IS 456 2000. So we have to calculate that due to concentrated load, we have to calculate that effective width. Instead of taking say 1 meter, we have to calculate that effective width, and that we can find out from this formula, and which is available also in the code. Similarly for the cantilever beam also. So we shall stop it here, then we shall continue in the next class the slab. I think we shall take few more classes for slab. We have one more, that is your say two-way slab also. This is called one-way slab. Similarly we have two-way slabs. Okay.